In Chapter 2.3, we now will introduce to you a special type of density curve. And this special type of density curve is otherwise referred to as the normal curve. At the beginning, right up top, it has just the definition of what a normal distribution is. A normal distribution is simply a density curve that's symmetric. Okay, so left side and right side are going to be balanced. It's single peaked, meaning that peak's going to be right in the center, and it is bell shaped. Okay, so it kind of looks like a bell. Now, down below here, we actually have pictures of two normal curves. You can see one that's a little bit wider and one that's kind of narrow. And what determines your normal curve is your mean and your especially the standard deviation. Notice how I have two symbols here, mean and standard deviation. Since it's symmetric, these are the measures of center and spread that we use. So we have a new symbol here. It's the Greek letter mu. It looks like a curvy M. And it represents population mean. So when we talk about normal curves or something that's normally distributed, if we give you the mean, it will be given to you with the symbol mu. The standard deviation is a lowercase sigma. So as you probably have seen in this class a little bit, we like to use symbols. And some of those symbols we like to use Greek letters. Okay? So this represents the population standard deviation. So now, what happens in a normal curve is where the single peak occurs is at the mean, and it's at right smack dab in the center of the curve. So you can see our means right here on both of those curves. Then what happens is your standard deviation will start to dictate how wide or narrow your curve is. If we remember, standard deviation is your average distance a given data point is away from the mean in a distribution. So how you find it on this normal bell-shaped curve, is this concept of what's called inflection points. And the main thing about inflection points is it just helps you with drawing your curves and labeling it. So what happens is your normal curve changes what we call curvature. So I know I'm sketching over it right now. But what happens is, those of you, if you remember, if you've ever taken pre-calculus, just out of curiosity, how many of you have taken a pre-calculus-like course here? So about half of you, okay? I know this is something we don't talk in Algebra 2, or if you've taken calculus. We'll talk about a curvature, how the curve will either be concave up, because the curve is pointing up, or it will be concave down, because the curve of it points down. Okay? Where it changes curvature is called the inflection point. And what's nice about the inflection point is where it changes curvature, that distance from the mean is one standard deviation away. So when I start to label and draw my normal curves, like if I draw a number line here and I kind of sketch a normal curve to the best of my ability, I know my mean is going to be located right in the center. Then I look at where I approximately change the curvature, curving up, curving down. That distance is one standard deviation. So the mean plus a standard deviation. Or, if I'm going to the left, the mean minus a standard deviation. So whatever those particular values are, I could actually write them on there. So now, what's nice about the normal curve is it has some unique properties to it that we have discovered, mainly through the use of calculus. Now, calculus is not required for this course, So, and we don't make you do any type of calculus concepts in here. Okay? But one of the rules with normal curves that I had to memorize, and we still want you to know this, okay? However, with technology these days, we can actually find these areas much easier. But it's still a nice rule to know and love, make your best friend, because you can use it as estimation skills, okay? You can start to estimate answers to questions that we will do with normal curves. This rule is called the 68, 95, 99.7 rule. Now you're like going, whoa, it's three numbers, 68. Second number, 95. Third number, 99.7. What those numbers correspond to is how many standard deviations you're away from the mean. The middle 68% of scores are going to be within one standard deviation of the mean. The middle two standard deviations, or I'm sorry, the middle 95% will be within two standard deviations, and the middle 99.7, almost all the possibilities or all outcomes in the distribution are within three standard deviations. Almost all. So down here there's kind of a picture that shows you middle 68%, middle 95, 99.7%. Okay? What I like to do to help students sometimes is even break it down a little bit further. So over here I'm going to draw myself a little nice normal curve. Here's my mean, right in the center. I'm going to go out 1, 2, 3 standard deviations. So I'm going mean plus a standard deviation, mean plus 2 standard deviations, and the mean plus 3 standard deviations. I'm going to do the same thing to the left, but instead of writing plus, I'm writing minus. So the mean minus 2 and the mean minus 3. So now, what happens in your normal curve, okay, is the middle from -1 standard deviation, that was weird that didn't show up, to 1 standard deviation, this area is 68%. But sometimes what I like to do is divide that by the line of symmetry or at the mean. If this whole thing's 68, I divide that in half, that's 34%. And 34. So all the scores between the mean and 1 standard deviation to the right is just 34%, or the mean to the left, 34%. Now I can do the same thing again for 2 standard deviations. So what I'm going to do is I'm going to calculate out these little areas right here. So to get those, if I think about the whole distance is 95. I've already accounted for 68. So these pieces right here equal 95 minus 68, or 27%. Because I've already accounted for the middle 68, so these two ends would be what's remaining. So 95 minus 68 is 27. These two areas add up to 27%. Divided in half since it's symmetric. So between 1 and 2 standard deviations either to the left or to the right, 13.5% of your data will be between those values. Now, to get the last two, I'm going to think about it like this. The whole thing right now is 100%. If I'm talking about 2 standard deviations, I've already accounted for 95. Now, if 3 standard deviations is 99.7%, if I do that subtraction again, 99.7 minus 95, that leaves me 4.7. So if I divide that, 2.35, 2.35. leaving me only 3/10 left in these little tiny tails. So this little tiny bit is only 0.15% and 0.15%. So if you remember in your CFU problem when we were talking about the baseball players, Williams and Cobb and Brett, and they were 4 standard deviations above the mean. They were even farther above 3. So you can start to see how they're like in the 99.99 percentile. Okay? Very rare outcome. So, how you go about using this graph becomes very important, like in an example like this below. I only use this if it specifically states to use the rule. Okay? So, in our example down below here, it says the distribution of heights of young women aged 18 to 24 is approximately normal with a mean of 64.5 inches and a standard deviation of 2.5 inches. Use the 68, 95, 99.7 rule to answer the following questions. So, if I look at A, it says what percent of women are taller than 69.5 inches? What I'd like to actually do is, since I have a series of questions with this problem, I'm going to draw a picture of the distribution. So up here, I'm just going to kind of draw a quick sketch of my normal curve where my mean is at 64.5. So I'm going to go 1, 2, 3 standard deviations to the right and then to the left. So to get the next score to the right, what am I going to add? Our standard deviation, 2.5. So this will now be at 67, 69.5, 72. Going the other direction, 62, 59.5, 57. So now, if I look at like this first question, it says, what percent of women are taller than 69.5 inches? I can go right on my curve. Here's 69.5. I'm looking at this area right here. So if I'm looking over here at this curve with all the percentages, that's 2.35% and 0.15%, which is 2.5%. B says, between what heights do the middle 68% of women fall? Well, that's the 68% of the rule. That's within 1 standard deviation of the mean. Okay. So we're talking the mean plus or minus 1 standard deviation. So we're talking 64.5 plus or minus 2.5. So looking at my graph here, I can actually see 62 to 67. So the middle 68% of women fall between 62 and 67 inches. Now the last one is probably the most challenging one of the 3. Says what percent of women heights are between 57 inches and 67 inches. So when I look at the curve here, here's 57, here's 67. So I'm trying to, in essence, calculate out that particular area. So if I think about 57, I'm minus 3 standard deviations. 67 was 1 standard deviation. So what I want to do is really add up all of these percentages. Because I'm going from -3 to 1. So I'm going, one way you could do it is go 2.35 plus 13.5 plus 34 plus 34. So So if you add all those up, I believe you get 83.85%. Now, it's not the only way you can solve it or figure it out. Some students like to go, well, geez, that's a large part of it. I could calculate out, what's left over, okay, and add those together and subtract from 1. So another way you could have done it was you could have said, well, I have 100%, and I have to subtract out this bottom tail, which is 0.15%. Okay. And then I also have to include this tail right here, which is 1 standard deviation above. Well, if this is 34, this here all adds to 16. That also gets you your answer. Sorry, I forgot the little percent there. So either way works. Alright, are we okay with this rule so far? Alright, now, the question then becomes this. What if I ask what percentage of women are less than 71 inches tall? Is 71 one of these values? No, it's not. So, since it's not one of these values, I know that it's probably going to be somewhere in between here, and I could kind of guesstimate, but I want to be able to find the exact proportion of women that might be taller or less than, say, 71 inches. So in order to do that, we have to come up with a process that can change any score, okay, so that we can actually calculate out that proportion. So, if we know if something is normally distributed, what we do is we convert it to a standardized normal curve. What a standardized normal curve does is this, is it takes anything that's normally distributed and we change the mean to 0 and we change the standard deviation to 1. It's our standard normal curve. Okay? This is the notation that you can use. N stands for normal, so you can write it as this, normal parentheses, mean comma standard deviation. So you'll see the standard normal curve written as N in parentheses 0 comma 1. Okay? So one of the things that we have done, okay, in this class, and I apologize, I thought I had all of this erased, but I guess I don't today. I know I did, but somehow it's appearing again. Okay. Is that we can take anything that's normally distributed and we can standardize the score. Remember how we were doing z-scores the other day? We were doing z-scores, I believe, on Tuesday? Yeah. Okay. What a z-score again is how many standard deviations is your score away from the mean? Well, if we think about the standardized normal curve, you're starting at 0. You're going to figure out how many standard deviations your score is away from the mean. Once you get that value, you can either use a table or your calculator to calculate out the areas. Okay? This is where this pink sheet with table A on it comes into play. How table A works is this. Okay? Table A calculates out your z-score. And what it will do is it gives you all the areas under the normal curve at a particular z-score, and it represents the proportion only to the left of the z-score. Okay? So for instance, could someone kindly give me a number between 0 and 3 with 2 decimal places? 2.22. Okay? So say for instance I'm looking at, I want to know what proportion of scores are 2.22 standard deviations left of the mean. Isaac.
Can you explain the -0 on this?
Negative 0.
On your pink sheet, you have negative 0.0.
Okay, yeah, I'll get to that.
Okay.
Think about it like this. When you look at your z-scores, can z-scores be positive and negative? Okay? Yeah. Positive are above the mean, to the right of the mean. Negative z-scores are left of the mean. So your areas are going to be less than 50%. Your areas on this side, positive, are going to be greater than 50%. So you can have z-scores that are negative, it's just you are left of the mean. Remember how, like, when we were doing the z-scores, Sophia's score was above the mean, Gannon's score was below the mean, because we got a negative z-score?
But so 0 would mean that you are the mean, right?
Correct.
So then how can you have a negative 0 and then a positive 0?
Well, because you'll see, okay, because how the table works, okay, is it all depends on the negative side or the positive side, okay? That table is not just for negative 0, it's negative 0.001, 02, 03, 04, 05. I'll show you how that works. They put the negative there so that you know you're to the left of the mean versus to the right of the mean, okay? So, for instance, can I at least do this example and I'll do a negative one for you?
Sure, can you do negative 0 for the next example?
I will do a negative side. That's what I just said.
Okay, but can you do negative 0?
Okay, so for the next one, I will do z is less than negative 0.02. Okay? Alright, so z is less than 2.22. Go to your table A right now, and what I want to do, you'll be at table A for a second, but what I'm doing here is I'm trying to find the area that's 2.22 standard deviations to the right, and what the table gives you, table A, is going to give you this area, okay, or this proportion of scores that are 2.22 standard deviations above the mean. So, when I look at table A, you have two sides of it. Okay? One of the sides is negative z-scores. So you'll see all these negative values. Okay? And then you'll see a side that has positive values. I'll erase that for a second because that was probably done in class today. If you're above the mean, go to the positive side. If you're below the mean, go to the negative side. So when I'm looking at 2.22, all of these values here in the table are the areas. Okay? And they basically give you areas for values from 0 all the way up to positive 3.49. So they will give you areas up to 3.49 standard deviations away from the mean. Our number was 2.22. So what I do is I go along this line right here at 2.2, because here's my z-score. So I'm looking at my z-score at 2.2, but I have a hundredths place too. Notice up here is your hundredths place. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So when I'm looking at 2.22, I'm actually going to the third value in the table, because this is 2.20, 2.21, 2.22, 2.23, all the way up to 2.29. Then we go 2.30 if we had to keep going. So our area here, I'm so close to, is it 0.9868? Yeah. Yours is easier to read than mine sometimes. Of course, my eyes are going these days. So like this area would equal 0.9868. So roughly 98.68% of the scores are at 2.22 standard deviations or to the left of the mean. Or above the mean, I should actually say. So on this one here, z is negative 0.02. Okay? So if I'm looking at my normal curve here, remember your mean is at 0, so negative 0.02 is going to be this area right here, less than. So I know this answer is going to probably be pretty close to 0.5, mainly because it's very close to half of my normal distribution. So to find that area, I go back to table A, but since the z-score is negative, I'm not on the positive side, I'm on the negative side. So now, I go down here, and the reason why the negative is there is because you can have negative 0.01, negative 0.02, negative 0.03, negative 0.04. Okay? So I'm looking at negative 0.02. Yeah, sorry, negative 0.02. So I'm looking at an area of 0.4920. So knowing how to find these areas using z-scores is very important. So what we're going to do, yes, the negative 0, 0 and the positive 0, 0 are the same as 0. That's why it's 0.5, because you're at the mean. Alright, so if we go to the bottom, there's 3 practice problems that we're going to do here together using table A. Okay. So, to get each of these problems, have a slightly different process that you have to do to get the final answer. You're going to use table A directly the same way, but you might have to do something with that area to get your final answer. Okay. I'm actually going to do question B first because it's the most direct and similar way that we have just done these previous problems. So, on this first one, or B, it says Z is less than negative 0.72. I always draw myself a picture. Again, z-scores represent how many standard deviations you are away. So if the mean is at 0, the inflection point is negative 1, I can estimate this to be at about 0.72. So I'm using estimation skills to draw approximately where my z-score would be. Now, a less than is a direct value that you can get from table A. Okay. So, I think you are correct. So negative 0.72 is that one right there, 0.2358. And that's the answer that I'm looking for. Oh.
Do you need to draw a picture or can you just write the answer?
You should draw a picture because later on in the problems you'll want to draw a picture so you know which area you're trying to find. Because take a look at A. It says Z is greater than or equal to 1.65 standard deviations. Because what's happening on A, 1.65, I'm estimating past the inflection point, and I want the area that's greater than. Okay. Now the thing with your table A is if I go to my table A right now and look at what 1.65 tells me, okay, 0.9505. Okay. It tells me 0.9505. And just to show you, I'll go to my table A. I need to go to the positive side. Need to look at 1.65. So 1.6, 1, 2, 3, 4, 5. 0.9505. Now, is that my area? No, it's to the left. 0.9505 is this area right here that's not shaded. So say that again. So you just subtracted from 1 since the area of a density curve always totals 1. So 1 minus 0.9505 equals 0.0495. And that's our proportion or the area we're looking for, 0.0495. Because we're subtracting from 1 because this is the area we want. Okay? So when you have less thans, you're getting it right from the table. When you have greater thans, you have to subtract from 1. When you have ones that are in between two z-scores, there's even a little more work than you have to do. So, when we're talking about scores that are in between, now we're talking roughly here, I'm just going to estimate negative 1.32 standard deviations to 2.15. Okay. So now, what you want to do is this. You want to get both table A scores for these z-scores. So if I'm looking at table A, okay, if I'm looking at the z-score equals 2.15, that gives me an area of, if I go to my table A, it's like 0.89 something, is it, or 0.9 something? Okay, so 2.1, was it 5? 2, 3, 4, 5. 0.9842? 0.9842. Well, what happens is this particular area is all of this 2.15 all the way. Okay. But do I want all of that? No, I want to cut it off right here. So what I'm going to do is subtract out that particular area. That particular area is found by doing the z-score of negative 1.32. So, look at my table A again. I'm now going to the negative side. Negative 1.32. Negative 1.32. You got it. So 0.0934. So now I need to subtract the two. 8908. So when you have a betweener and you want to use the table, you subtract the two values from table A. Come on.
For question B, why do you estimate that 72 right there?
How did I estimate that it was right there?
Yeah.
Okay, I know that where it changes curvature, which is about right there, is -1 standard deviations away from the mean. So I know it's just got to be somewhere close to it. Okay? Is it exact? No, but it's at least relatively close. Alright, so now, here's the nice thing, okay? Table A is wonderful, and I like to use Table A quite a bit, okay? However, technology these days is really nice, okay? And there is a command that you can do on your calculator to find these areas. And they are called, and that command is called normal CDF. To get to it, we use these keystrokes. Second bars, number 2. So, what you have to enter in, however, is a lower bound z-score and an upper bound z-score. So if I go back to these problems right here, if I want to do this first one on my calculator, what I would have to do is I'd have to go normal CDF, and now I have to enter in two values. A lower bound z-score and an upper bound z-score. Well, for this particular area, my lower bound, my lowest possible score is 1.65. The problem is, do I have an upper bound z-score? No, it keeps on going forever, just like some of my teaching lessons. Thank you for laughing at that. Well, we just need to enter in a very large number. What I tell students to do is when you write it, just write a few nines with a dot, dot, dot. And again, note that this is lower bound, upper bound, so that we know what those values represent. So on my calculator then, I can calculate out those values. So second vars, you can see normal CDF is number 2. 1.65 comma. Now, honestly, 19 is enough. I'll enter in 3 but just by habit, but if you enter in 2 or 1, you'll notice that you'll get the exact same value as I do. Is this the exact same decimal? If I round to 4 decimal places?
Yes.
0.0495.
Is 1.65 the lower and 999 upper?
Correct. For this one, yes.
I got 0.950.
Did you go from, what did you go for your lower bound to your upper bound?
Negative 1.65.
Why were you going negative?
That's, I don't know.
Okay? Again, that's why, so if you're going to use the calculator, you got to make sure you're putting in the correct values. It's not negative, it's above the mean. That's why it's positive. And it's on the left side, so it must go first. The right side goes to infinity. So now, if I do the second one here,
You just do negative 999 for the lower.
you got it. So for this one, normal CDF, the lower bound is negative infinity. So I can just go negative 999, comma, to my z-score, negative 0.72. Let's see if we get, whoops, I put 7.2, and it should be 0.72. Do you get 0.2358? Up. And second vars. Oops, of course it helps if I hit vars. So I get normal CDF. Okay. Negative 999, comma, negative 0.72. Make sure you're using the negative symbol, not the subtraction symbol. Gavin.
My calculator has the option to change like the sigma and mu and pace. Does that matter at all?
Okay. What I would do, that does matter. Right now, your calculator is probably on, has your stat wizard on. So what you should do is do one of two things. If you're going to use normal CDF, change your mean to 0 and your standard deviation to 1 for all problems. Or do this. Go go to your mode, scroll all the way to the bottom. Mine probably won't have this because mine's an older version, but you're going to see something that says Stat Wizard. Turn it off. Okay? Because what the Stat Wizard does is it gives you a menu, or it's like a menu style where you put in values and then it puts it all in for you and then you execute it. I think it's a little clumsy, but some people like that version. I like the other one. I like getting it to it directly. Okay? Alright, so we get again the same value. This is where it's really nice. On this last one on this page, this is where you just go normal CDF. Lower bound was negative 1.32. Upper bound was 2.15. Okay. Do you get 0.8908? Yeah, it's actually really nice. Students like these ones the best because they actually give you a numerical value for the lower bound and upper bound. Unlike the other two where you have to have one of them be infinity, so you're estimating infinity. Alright, so now, the last thing that I want to talk about, if you flip to the last page of your notes today, we just have one more example. And these examples have us do the reverse. We're working backwards. Okay? Instead of, okay, finding the area under the normal curve, we're going to be given the area, and we want to find the corresponding z-score. This is unbelievably important when we want to, like, for instance, find out, you know, what GPA would put me in the top 10% of my class, or what ACT score would I need to be in the top 5% so I get the big scholarship. Okay? So you can, doing this will help you be able to calculate it out. So how you go about doing it, again, the picture helps a ton. So on this first thing it says, find the z-score that corresponds to the 78th percentile. So what I'm doing is I'm drawing a picture. 78th percentile. What it's saying is the areas under the curve is at 0.78. So somewhere out here, so that this area is equal to 0.78. I want to know what z-score corresponds to it. So now, to do that from table A, you're working backwards. So, if I go to table A, since I know that that area is more than 50%, am I doing a negative z-score or a positive z-score? Positive. So I can go right to the positive side. Excellent. Okay. So now, I'm looking at my areas, because that's the information I have. I have this value. I want the column value, or my z-score. So I'm looking on here going, all right, what's values the closest to 0.7800? Well, as I start to scroll here, it's going up, this is going up, 0.77, 773, 776, 7794, 7823. There's my closest one. So the z-score that it corresponds to intersects at these two values. That's a z-score of what? 0.77. So from table A, our area that we looked at was 0.7794, which was my area, corresponded to a z-score of 0.77. I chose the one that was closest. So this is closest to 0.78. Now, here's the nice thing again about our technology and our calculators. Okay. On your calculators, okay, you actually have a function, and it's in your notes on the previous page. I'm just going to summarize it here. And how it goes is this. Inverse norm of an area will equal a z-score. So to get to this inverse norm, I'm actually going to jump back to the page because I want to put this in your notes. Inverse norm of a percentile, or the area, is equal to the z-score. The command on your calculator, it's very easy because it's right below normal CDF. So second var's number 3 is this inverse norm. So what I can do for this particular one, inverse norm of 0.78 is equal to, and what's nice at least about the inverse norm part, second var's number 3, 0.78, it gives it out more than 2 decimal places. 0.7722 if you wanted to go out 4 decimal places. Again, this is my z-score, which is basically telling me my actual score that I might be looking for is 0.7722 standard deviations above the mean. So if I know the mean and the standard deviation, I can find out that score. Let's take a look at the last one. And this is why a picture is so important. 60% of all observations are greater than Z. Well, the information they give you here is this. It's not 60% or less, 60% or more. So you're actually where this area is 0.60. But this, in order to find Z, this is the area you have to use. Because table A and inverse norm are always doing less thans. So if I want to use this area, what is it?
40%.
Yeah, 40% or 0.40. So I'm going to show you both. Table A. So again, if I'm looking at table A, whoop, since it's less than the mean, I'm going to use this one, or the negative. I'm looking for the one closest to negative 0.40. 0.4013 versus 3974, that one's closer. So negative 2.012345. So table A was, the closest was this value, which corresponds to a z-score, whoops, of negative 0.25. On the calc, you'll probably like the calculator a lot better. You're just going to go inverse norm of 0.4.
Are we gonna have the option of doing it either way, or are you gonna like say?
Nope, you'll have the option. But if you use your calculator, please make sure, oops, second bars, that you tell me what the values you're putting in.
Okay.
So you'll see me on these problems where I'll actually like say LB, UB underneath them for lower bound, upper bound, or I'll say like area underneath these values. So whoops, I apologize, it's not negative 0.25. Second vars, number 3, it should be what? 0.40. I'm glad I caught that. Which is the negative 0.2533. So again, that's your z-score. So like if I'm using it on the calculator, what I would just want you to note here is that that's the area or the proportion or the
So
percentage.
it doesn't matter if you put it in negative or not?
For
Since you're
the,
using, since it's below the,
well, it's below because this value is less than 50%.
alright, so it automatically becomes the.
Yeah, it'll change the z-score to the negative.
Alright.
Asia,
So I put the wrong number in, but I got the same number. I put 60.
you put 0.6 and you got the positive value of it?
That's why.
That's why.
Okay, so when you were doing the one you do earlier, like the normal CDF,
Yep,
the answer you get from that is area.
is area, yep. And on these, you're given the area
And
and
you're finding.
you're finding the z-score because you're working backwards.
So.
How do you determine? This is not a percent, this is the z-score. This is telling me how many standard deviations a score that is 40% away, or that is at the 40th percentile is away from the mean. Okay? So it's basically telling you that you're to the left, 2.25 standard deviations to the left if you're at the 40th percentile. Yep. All right, any other questions? Yes? How did I find it on the table A? So the question is, how did I find this on table A? So again, what I'm looking for is the area closest to area closest to 0.4. So when I go to table A, I'm looking down here, what is the z-score that corresponds to it? And it was negative 0.25. The nice thing about the table is, you know, it gets you a 2 decimal answer pretty quickly. It's not too hard to use. It's not exact because you have to kind of round it. Okay? The calculator is nice because it'll give you the exact value for you. All right, any other questions? All right, I know we don't have a lot of time, so I want you to at least get started on the CFU packet.